things together. On the other hand, quantum is inherently parallel. However much information I load can operate on all of it at once with one piece of hardware. This makes it extremely efficient. You've, of course, heard the exponential speedups and all of that, but it's also the case that it's extremely compact in its representation. So I need very few pieces of storage to hold a lot of data, a lot of information. And it doesn't take long for me to reach things that are just impossible classically. I can store more information and then operate on it all at once than you ever could with a classical machine. So it's on a completely different scaling. And of course, I'm telling you all the good things first. We'll get into the bad things, don't worry. But let's start at least with what looks good and why it looks promising and why some of us are working in this area. Everybody here is familiar with Shor's algorithm. I am not going to go into it today, but it was a good example of something that intrinsically works well in a quantum computing paradigm because, and you'll see as we get into this later, it has very little input, very little output, but a heck of a lot of computing. And that's really what you're looking for the types of problems you want to solve. Quantum computers will never replace classical computers. There are things it's good at and things it's terrible at. And so we want to pick the right places where you actually get a bang for the buck. But we all know the types of speedups we'd expect from Shor's algorithm as an example. This is an estimate on a medium speed, relatively large quantum computer, what you could expect for 2048. But there are other areas. Over 50% of the world's supercomputing time is spent on problems that you could argue are better done on quantum machines than classical. We simulate a lot of chemical systems, a lot of materials, but everything we can do, even to the fairly large molecules, are in the first couple of rows of the periodic table. These are organic molecules. And the reason for that is the orbitals are all local. They all just sit. sp orbitals all sit outside. As soon as we get down into metals, we get into the third, fourth level of the table, they become non-local. They zoom all the way in from the nucleus all the way out and cut across all the other orbitals. We can't do them. So when we get to molecules we really want to do, like the one that's up here is the one that does nitrogen fixation. We'll spend a little time on that later. It has 6 irons and a molybdenum in it. You can't do it. It's intractable on a classical machine. There's no way to analyze it. There's no way to model it. There's no way to synthesize a replacement for it. And when we look at these types of problems and say, well, gee, classical gets faster and faster, we say, okay, we'll look at how this scales with the molecules, and we look at the current scaling, and then we look out 10, 20, 50 years of projections for classical computing. And the problem with exponentials is they don't move much. I mean, you'll get some improvement, but you're not going to move that far. You need something that intrinsically has a different scaling, and that's what we're talking about. So let's do some basics. I think it's probably a good idea. I'm sorry if I bore some of the people in the room, but it might be worth explaining what the real fundamental differences are. So in classical, we'll start with a bit, 0 or 1. People like to say that a qubit is, oh, it's both 0 and 1, there's some probability. It's actually a lot more than that. That alpha and that beta are complex numbers. So it's really on a 4-dimensional sphere. And I can put a lot of information into that 1 qubit. So it's actually called a magnitude instead of a probability because it can go negative. But when you square it, everything will sum to 1, it's back to being a probability. So I can read values out and get probabilities out, but we're actually operating on this block sphere, which is this 4-dimensional sphere that we store our unit of information in. So that's where we start. Classically, we do gates. Put an input in, put it through a NOT gate, it flips it on the way out. Not very different on the quantum side. We just use matrices to describe how we move those complex numbers. So if I have alpha is the magnitude of it being a 0 and beta is the magnitude of being 1, multiplied by the matrix on the left, and I flipped it. That's my NOT gate. So you have equivalent types of gates that you can do quantumly. And as we get more complex, here we have an XOR gate. We normally would use truth tables. Here, well, we already have the matrix description, and the controlled NOT gate is an XOR. If you have a 0 on the control line on top, it does nothing to the qubit on the bottom. The qubits are going across top and bottom. And if there's a 1 on top, it flips it. However, it's doing all combinations at once. It's a matrix operation. So you're just doing linear algebra. In fact, that's all this is, and you'll see a couple examples later. But one of the big differences, on the left, I have 2 inputs and 1 output. I have no way of going backwards. I have no way of going backwards through the system, which means I've lost information, which means it dissipates. This means it eats heat, or generates heat rather. It's inefficient in many ways, versus here, everything is reversible. And so by doing that, we're able to build very efficient systems that have unitary operations, and all the gates that are truly quantum go both forwards and backwards. I can take my whole calculation and uncompute it. So this makes for an interesting way of writing software, because now you have to start thinking about doing things so they're fully reversible as you go. On the other hand, I did say I'll start talking about the negatives too. When you write classical software, you make temporary copies all the time. You do what ifs, you say I want multiple answers for something, and you just say, okay, do this calculation, pull it out, okay, erase that, come back, but I can't erase. Remember, I've got this problem, it's all reversible, it's all describable through the entire system, so I can make all the copies I want, but they're linked forever. If I touch any one of the copies, I've done that on all the copies. So there's no independent copying. This is called the no cloning theorem. Noise. We have noise on classical systems. We put parity bits on memory, Hamming codes, all sorts of error correction codes. We also have noise on the quantum side, but it's much worse. Remember, we're in this 4D space that we're trying to keep this thing alive in. We're trying to keep exact angles. And it takes a lot of qubits pulled together to make one that lasts for a long time. We'll spend some time on that too. Back to the good news. Classical, okay, I've got a 32-bit register. I can hold one number from 0 to 4 billion. If I have 32 qubits, I can hold 4 billion values in 32 qubits. So immediately we get this massive increase in storage. But more importantly, when I take two 32-bit registers and add them together, I've added the two numbers. On the quantum side, I've added 4 billion numbers with one operation. And this is where the big speed up comes in. So this hand in hand, the storage and the speed up together is what makes this difference. Classical, input's linear, output's linear. You've got to load the data, and you got to get it back out. You can't go better than that. Quantum is actually significantly worse. You load it linearly. That's okay. I've got to get the data in. The scaling isn't that different. But when I read it out, remember I have 4 billion values in 32 qubits, I get one value out. And that value is probabilistic. So I do a computation, I've got these 4 billion results, and now I go to look at it, and I get one out. It collapses to a classical state. This is Schrodinger's cat, where by looking at it, it all falls into a classical state, and I get one number. Now, the number I get out is probabilistic based on its magnitude. So if I do a computation that makes the answer I want high probability, then when I read out, I will get it with high probability. But now I want another answer. Remember, everything was reversible? Well, we just broke that by getting an answer out. We have to go back to the beginning and load everything again. Let's say I want to page rank the internet. I load all the web pages in, I run the algorithm. What comes out is the page we landed on. Great, I want another page. Load the whole internet, go all the way through, get a page out, and keep sampling. So that whole exponential speed up of getting the page rank is destroyed by how many times I have to load a ridiculous amount of data. Not a good problem to solve. If, on the other hand, we were looking for one page with a specific characteristic that was really hard to compute, this would work really well. I don't mind loading the web once to get the answer that I want. So you have to change the question you ask. You can't just solve every problem. There's another piece here. I started talking about noise a little bit and error correction. Some of the qubit technologies, and this is majority of the people are building, scale very well. They're made with standard semiconductor fabrication techniques, and I can build lots and lots of qubits, but they're noisy. Error rates around 10 to the minus third. What that means is I need anywhere from 1,000 to 10,000 physical qubits to make one logical qubit, make one that lasts as long as I want to compute with. So when people say, oh, I only need 200 qubits to solve real-world problems, multiply by 1,000 to 10,000. They're talking logical qubits. They almost never tell you the physical qubit number. And this gets back now to the hype. So I need 200,000, 2 million qubits before I can really start solving real problems. That's a problem in and of itself. On the other hand, there are qubits that scale to lower and lower noise, which looks really good, but they don't scale in terms of numbers. You can make dozens of them, and that's about it. So we have this bad trade-off between, do I want a lot of qubits, or do I want good qubits? Our approach, we're trying for the best of both. And this is where we get into topological quantum computing, which is what Microsoft does. So before everybody's eyes glaze over, because it's what usually happens when I go down the topological route, let me give a little inspiration.
There was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one man did, because he's the only guy who caught on before he wrote his paper. But after people read the paper, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics. I'm going to tell you what nature behaves like, and if you will simply admit that maybe she does behave like this, you will find her a delightful, entrancing thing.
So that's how I feel. And we're going to start with an interesting story. I don't have time today to tell the story of Ettore Majorana, but to be honest, there's actually murder mysteries and plays and all sorts of things about what happened to Majorana at the end of his life. But just before he disappeared on a ferry, he published a monograph about a topological state of matter. And what it had to do with was an electron or a fermion that was actually split and could live in two places at once. Now, I'm not going to quote Monty Python. But the Majorana was split such, we call it now a Majorana fermion. It was split such that it's still one electron. You can't have one half. It always has to exist, but it's physically separated in space. Very bizarre. It actually turns out these might actually exist, not just be a mathematical nicety. The Large Hadron Collider, now that it's found the Higgs boson, is looking for Majorana fermions because they think this may be what makes up neutrinos. So that's kind of a side note. And it turns out we couldn't use those particles anyway for computing for a mathematical reason. But this idea kicked around since 1937. Nobody did that much with it. It was interesting. And then at the end of the 90s, Alexei Kitaev came up with this idea of using these particles, if they existed, for computing. And he got together with Michael Friedman at Microsoft in 2000, and they started working on this topological quantum computing approach. They got far enough along. I should mention the diagram has to do with moving these particles around each other is how you compute. You braid, just like having macrame. You have a whole bunch of qubits and you move them around each other, and at the end you've done your computation by braiding them. That's going to be important later. But they got together, they started progressing on this, and they got far enough that in 2006 Microsoft created Station Q, specifically to build a topological quantum computer. This progressed until 2012, when we had the cover of Science magazine that we'd actually produced Majorana particles, actually quasi-particles in the lab. I should also mention, there are a lot of things I'm using terms that I'm not explaining. Feel free to grab me after the talk. I'll be here all morning if anybody wants to get more detail on anything. But the right is an actual scanning electron microscope picture of the experiment. The left is an artist's rendition. But we showed this in 2012, and then there were 5 arguments why they might not be Majoranas. All 5 have now been debunked, and we're now at 2018, where we've reached the point that we know we have the particles. You really now want to start engineering. You want to start building a system out of them. And that's where we are today. So what are these things? What do they actually look like? If we start with a nanowire, the thing you saw on that diagram or on that SEM, and we're going to leave one channel open. So we're going to allow enough room for an electron to move, moving one channel of electrons through. And what you see in the gray at the top is an electron. It has a real and imaginary part, and they're going to line up down the wire, all the way down the wire. And since you're allowed to have a spin up and a spin down electron on top of each other, you really get two of them. You get a spin up and a spin down, and they sit there along the wire. This can be an insulator, conductor, it doesn't matter. Now we're going to make this out of a specific set of materials, and we're going to make it very, very cold. And the spin up and spin downs bond together. They become what's called a Cooper pair. And you now have a superconductor. These are all the superconductors you've seen, the demonstrations. This is every type that's out there is an S-wave superconductor. But it's not the only type. There's actually 3 different types of superconductors that are defined. And if we use a different set of materials, something that has what's called high spin-orbit coupling, and a really strong magnetic field, a Tesla, so a big magnetic field, these will pair slightly differently. They'll pair to their neighbors instead of pairing up and down. And you'll notice what we have. Hello. Where are we? There we go. We have a real part on one end, and we have an imaginary part on the other end that aren't bound to each other, but they're also not bound to anybody else, and they become a single electron that's split at each end of the wire. Now, why do we care? The problem with all those other qubits, the problem with decoherence, why they fall apart, is the Schrodinger's cat thing. If they're observed, they fall apart. But observed doesn't mean a human looks at them. That's the problem when people describe that thought experiment. What it really means is anything in the universe interacts with it. Cosmic ray comes in, another electron, a photon, anything hits the qubit and it decoheres. Here, you hit one half of that electron, well, nothing hit the other half. So all you need to do is encode your information with a little bit of redundancy, and your qubit can last virtually forever. This is what's really cool about this, is you can build qubits that have ridiculously long lifetimes. It's the same way of thinking of writing with chalk versus knotting string to keep your numbers. A windstorm, rainstorm comes up, the chalk's gone, but the knots survive. This difference in topology is what makes the difference we're talking about and makes this data survive. So what does it do for you? We have materials in the lab where they stay coherent for a minute at a time, and we're early in the process. Most of the qubits out there last tens of microseconds, excuse me. This makes the real difference is down in the error correction cost, where for everybody else I said it was 1,000 to 10,000 physical qubits to do a logical qubit. For us, it's about 10. So when I say I need 200 qubits to solve real-world problems, for us that means 2,000. That's not such a scary number. Trying to get to 2 million is another problem. And so when it comes to the engineering side, the readout, the control, the fridges, everything we need, you just became several orders of magnitude easier to actually build the machine, provided you have the qubit. I also said you wanted to braid. That's how you did the computation. But there's a problem there. You have to move them around each other. It's really hard to engineer. There's also problems with them falling apart because you've done it too fast. You want to do gate speeds. There's all sorts of technical reasons that braiding is really hard to do. So we're going to take a cue from the British fleet in 1588 when they sailed out and destroyed the Spanish Armada, because they figured out they could sail into the wind. And the Spanish believed it was against God and nature and it was impossible to do, and that was what happened in the battle. The sailing into the wind is due because you have two ways of projecting the wind vector. You have a sail and you have a keel. And as soon as you can measure or project in two directions, you can actually move a vector to any direction that you want. This lets you go into the wind. Well, we can do the same thing with the qubits. We want to rotate the state. We want to move around that sphere that I described. But I can do it just by measuring various points. And so that's exactly what we do. This is from the paper, if anyone's interested, this is the main paper that describes the systems we're building currently. And the qubits look like these H's on their sides. They have 4 Majoranas. These are the red dots at the ends, and then they're put together into a network that lets them couple. Up and down, the orange happens to be a semiconductor bus that lets them connect to each other through quantum dots. But what's interesting here is because of the way it's set up, we can define axes where we're going to say this is the z-axis if we measure across here. This is going to be the x-axis. This is going to be the y-axis. And now we can rotate this qubit to all different points on the sphere just by measurement. Again, good news, bad news. That's the good news. 100% accuracy. I don't have to worry about rotation angles. Just the measurement gets me that gate, the different gates we were talking about. Problem is, we're missing one gate. And that one gate can't be done with this type of particle. It's called a pi/8 gate or a T gate. And without that, you're not universal. So what's interesting here? I mean, everything up to this point led to, okay, now I have something that does everything I want, but I can't compute anything useful with it. Well, we know a technique that will take approximate T gates and turn them into good T gates. It's called magic state distillation. This is an example of one of the circuits. This one, the blue dotted boxes take 15 bad T gates and create at the bottom one that's cubically better. I can also nest these so I can go as high as I want. There's also better circuits than this one. This is kind of the canonical standard one. But the important thing is we do a non-topological operation to get the bad T's. They're going to wiggle around. They're not going to be accurate. But then we can distill them out. Yeah, we're going to have to spend 90+% of the machine making T's. But then we can rotate to any angle. Everything's topological. And the circuit itself that takes the T's and makes them better is also topological. So everything's protected. Everything's good except those input bad T's that we knew were bad. So we have a way to solve the other problem with this approach, which is making it universal. So we'll take this hand-drawn diagram, we'll put it into our system, and the system will generate out its own version of the diagram just to show that we read it in and read it back out. But now we'll go to the next level and compile it into this measurement only. So these have standard gates. Now everything that's left over are just measurements, either single or 2-qubit measurements. And then we're going to take those measurements and we're going to lower them down to actual devices. This is a SEM of a device in our lab that is the metaphorical child of one of the diagrams that's in that paper that I've been referencing. But now we'll take it and we'll put it in different geometries at the bottom. We'll figure out how we're going to hook them up, what the connectivity is, which qubits can talk to which qubits, and then we start simulating the circuits, and we can look at what measurements we need, how we have to move the qubits around with the states, the efficiency, the packing, all of that. So we've built a software stack from the very top to the very bottom. I can take a circuit, go all the way down to the hardware, and look at what I need for control, what I need to actually run the system, and I can actually play with different geometries and different types along the way. So we're really close to doing the engineering as opposed to doing the research. And I normally won't say how close, but since my vice president decided to do an interview publicly and quoted, we will have a qubit by the end of the year, and we will have a quantum computer that will be available in 5 years. I guess those are numbers now I should quote, because I've been told, make sure that happens. And I'm actually more worried about everything but the qubit than the qubit. We've had all this time to develop the technology, to figure out the research, to look at it, that we'll have a qubit or we won't, but it's no two ways, no other way. Either we will have a qubit and we continue on this, or we won't. So far, we have no negative evidence, so I'm assuming we'll have a qubit. But now I got to control it. Now I've got to do that error correction. Now I have to prepare and read out, and I have to cool it. I have to do fridges. I have to do materials. I have to do classical computing as close as I can to the quantum plane. And there's problems here. For instance, CMOS doesn't work below 40 Kelvin. Okay, but I want to run at 4 Kelvin. That's where liquid helium sits. And I got to get to 15 millikelvin down there, which is 100 times colder than outer space, is where the qubits live. So I need ways of talking, say, between them. Okay, now I need superconducting wiring, and I need a way to be able to transfer signals but not heat, because that'll heat up the bottom. Oh, I've got to do lots of computing at 4 Kelvin, but I said CMOS doesn't go below 40. I need superconducting classical logic now. I also need, say, at 77 K, where liquid nitrogen is, to run my normal classical machines. They'll run there. They're above 40. But now I get to get signals between the two without, again, heat pollution going down and good signals coming up and going down. There's a massive engineering problem here. This is what I actually do. I'm an engineer. I'm not a theorist. I'm not a researcher. I get to play researcher once in a while. But I'm an architect. I build systems. And so what I'm trying to figure out is how we practically pull all this together. If you look at some of the major efforts out there, some people have announced some really impressive numbers of qubits. But then you look at the number of coax lines going into, this is not one of our fridges, this is somebody else's, they have a lot of coax lines going in. Every one of those lines heats up the fridge. Plus they eat up a lot of space. You're almost at the limit of what you can put in a fridge before it's too hot and it doesn't fit. But now you want to go to hundreds, thousands, tens of thousands of qubits. You can't bring the signals in from room temperature. You can't do this sort of solution. It all has to be re-engineered. So we look at it at 3 levels of abstraction. At the top, we have a quantum programming language that lets you abstract things away into libraries, and we'll talk a little bit more about the actual software stack. We get down into the machine code, we have the gates that we mentioned. We're going to talk a little bit about how they go together. And then we have the devices and materials at the bottom. We have to grow our own materials. We have to build our own devices. We do this all over the world. This is the first day of my 3-week trip. From here, tomorrow I'm at meetings in Delft. Then I go to Copenhagen. Then I go to Purdue. Then I go to Sydney. Then back to Redmond. Yeah, we've got labs all over the world. My job is to be there every few months at all of them and make sure everybody's working together to build everything together. But our first piece of the whole puzzle came out recently in the Microsoft Quantum Development Kit. I'd like to spend a little bit of time on that. It has a high-level programming language. What's unique about this compared to saying, well, why yet another programming language, is this is a fully supported Microsoft language. This runs inside of Visual Studio. It's integrated. It has simulators, debuggers. It will be supported over time. It is something that we will grow through all the simulation models and then finally into the hardware. And it's not just our hardware, it's agnostic. So we can run this with any quantum hardware out there over time. We have, as I said, the simulations that are both local and cloud. We'll talk a little more about that. And then extensive libraries. All of the quantum algorithms that are known, we have examples in there. We have library support. You don't have to write any of that from scratch. It all comes with the system. So let's do an example. This is the hello world of quantum called Teleport. It is. I want to send a message from Alice to Bob. Alice and Bob start out together, and I'm going to do this from a linear algebra point of view to show you there's no magic here. What quantum does is very straightforward. It's just straight linear algebra. It just can do it really well. So what you see is that alpha and beta, that the qubit comes in, alpha is 1 and beta is 0, so we're sitting at 0 for both qubits at the beginning. Alice has a qubit, Bob has a qubit. And we can either look at them separately, or if you multiply it together, you could think of that as state 0, 0, 0, 1, 1, 0, 1, 1. So state 0, 0, both qubits are in 0, is why there's a 1 in the first state. And the square of all the entries will always sum to 1. So when you see 1 over square roots of 2 out front and so forth, they're to normalize the vectors. So the vectors are always normalized. And now we're going to flip the first 0 on its side. So we flip it to the equator, that's the Hadamard gate. And we now have the state that's shown. So we basically have one qubit still in 0, and the other qubit is half in 0 and half in 1. Now we're going to entangle the two. So the C0 gate entangles them. What you see there is the only ones are in 0, 0, and 1, 1. If one qubit is a 0, the other qubit's a 0. If one qubit's a 1, the other one's a 1. But you don't know which they are. They're equally likely. But if I measure one of them, the other one is instantly determined to be the same thing. That's important to keep in mind. Also note, this can't be factored apart again into two qubits. Once they've been entangled, that state can't be separated. And this is where all that computational power comes in, because now we can actually do things across all the qubits at once as we play. So, Bob now goes to the other end of the universe. He just disappears. He's gone. Takes his qubit with him, and somebody comes to Alice and say, here's a message I want to send. This AB message for alpha and beta. And so we entangle that with her qubit. Now here's the strange thing that happens. At this instant, not only did she entangle it with her qubit, but it's entangled with Bob's as well, because they were entangled. Remember, no independent copying, everything's fully entangled. That means A and B made it to the other side of the universe instantly. Okay, isn't that a problem? I mean, relativity and all that, speed of light. Well, that has to do with information. Bob can't extract A and B at this point. It's there, but he can't get it out. And again, this is why I like this as the quantum hello world, because it's about as quantum as you can get. And if you make teleport work, by the way, in your simulator, everything else works. Guaranteed. This is about the hardest thing you need to do, and it only takes a few gates. So now we've reached this point where the data is there, but not the information, if you prefer. If Bob was to read his qubit out, he has no idea what A and B are from the original one. So what Alice is going to do, she's going to flip her qubit back so the basis is the same, and now we move this back. You see this whole thing is filled with A's and B's, and she's going to measure her qubit. She's going to make them classical. So she measures them out. Now, when she measures them, either qubit could be 0 or 1, 50% probability. She has no idea which of the four cases, 0, 0, 0, 1, 1, 0, 1, 1, she's going to get. But when she does that, that fully determines what Bob's qubit is. Again, other side of the universe at that instant. But Bob still can't get it out. He doesn't know which is A and which is B. She has to send those two bits of information across the universe to Bob. So no information is transferred until slower than the speed of light, or at most speed of light. Those two bits are there. He applies his X and his Z gates to say which directions to flip them, and now he's got A and B back. So we didn't violate any laws of physics along the way, but we had instantaneous teleportation, sort of. And so this is a great little example, because this is kind of a fundamental, if you get all of this, you've got the fundamentals of every quantum algorithm out there. You've got the entanglement, you've got teleportation of information, you've got basis changes, you've got classical interactions with quantum, everything's in here. So let's look at this. This just says, yes, it's linear algebra. So let's look at this from the language point of view. This is QuArC, which is our top-level programming language for this. And we can create a teleport function that we say, oh, we need to allocate an extra qubit from the two from Alice and Bob that came in. We can allocate registers. We can provide quantum gates, apply them to the qubits. All of this looks like what you'd expect. This line's more interesting, even though it doesn't look, very different. The M is taking the measurement of the quantum state, making it classical. Then we're doing a classical if statement and then applying a quantum gate. QuArC completely understands both quantum and classical. For those of you who had used Liquid in the past, Liquid only understood quantum. This is a full first-class programming language. It does everything you could want classically as well as quantumly and knows how they interact. It can optimize across them. It can figure out how to divide in that fridge things that go at 77 Kelvin, 4 Kelvin, 15 millikelvin, 300 Kelvin outside in the cloud. It figures out what's quantum, what needs to be controlled. It understands resources. It can do all sorts of optimization. So this is just a little example, but it gives you the idea of the power of what you can do with this programming stack. So what we've built is something that has this top-level programming language, a whole bunch of libraries that go with it to make your life easier. You can also use any classical host program you like and talk to it. It's a first-class classical language. If you want to use C++ or C# or Java or anything else and you want to call it from QuArC or vice versa, you can. That's not a problem. And then we have a classical runtime that has a local simulator, ships with it, does about 30 qubits, It will do more, but again, you need more memory. 30 qubits, you're going to need about 64 gigabytes of memory, which is okay for a desktop. But one more qubit, you have to double the memory. One more qubit, double it again. So you very quickly run out of memory. So we say 30 qubits is probably your limit for one machine. We also have a cloud simulator version that does over 40 qubits, distributed over 1,000 machines in the cloud, because it grows, again, really quickly. Tracer is kind of interesting. I can do all the qubits I want, tens of thousands. It doesn't actually run the algorithm, but it tells you resources. How many gates? What can be parallelized? What goes together? What sort of noise models will affect it? And on and on and on. This lets you scale big problems. When I have a couple hundred logical qubits and thousands of physical qubits, Tracer will tell you how it will run, how long it will take, what will actually happen. And then on the other side, we have cryo control. So we have another open source system called QCodes, which is also available, that runs laboratory equipment. So QCodes is a Python system that lets you sit there and run these experiments in the fridges. We can compile into QCodes and have it talk to your quantum hardware, or eventually we actually have runtimes that go into the fridge at all those different temperatures, and we compile directly into all of those. So there's pluggable backends for the system. You put all sorts of different things in, and finally your quantum computer winds up at the bottom. The initial release of this whole system was December 11th. There was a new release last month, or actually no, sorry, a month and a half, February 26th, that's multi-platform, Windows, Mac, Linux. There's Python interrupt. It's now has an MIT open source license on it, so you can go in and party on to your heart's content. It's also available as a Visual Studio plugin, a VisX file. So this lets you plug it in and then fully integrate completely with Visual Studio. It's also available through GitHub. So all your favorite ways are available. Here's an example of inside of Visual Studio Code, which is a nice multi-platform editor that's very lightweight compared to all of Visual Studio. And this is running on a Mac. I just wanted to show that, yeah, all the interop is there. Everything works any way that you like. For the Python example, here's a Jupyter notebook where it's embedded inside of a Jupyter notebook, and you're doing some tomography work here. And since this is a crypto conference, it's not my field, but I felt I'd better do something. So I went to Martin Rottler and said, give me something, please. So here's his favorite hidden shift example. So we got a function f. We're going to shift it by some amount, call it g, and we want to determine what the shift was. And it's not a trivial shift. This is on vertices of a hypercube, and you're trying to figure out exactly which vertices you shifted on, all that sort of thing. The actual quantum algorithm is very straightforward, very simple, but it's a heck of a lot of computation to do classically. So this is a nice example. And what we're going to do is start with, it's hard to see on here, but the upper left, there's one, the guy turned on, that's the 0, 0, 0, 0 state. So we have 8 qubits here. There's 256 blocks, you see, that's the 8 qubits. And we're in the 0, 0 state. And the first thing we're going to do is spread everything across all of them. So they're all equal probability. All 256 possible states are all equal probability. Now we're going to take our function f, and I'm going to shift it. So just to show you, it's non-trivial. Here's f, here's g. And we're going to apply g to the system. And then we're going to take the spectrum of it, take a Fourier transform. We're going to convolve it with the original f. We'll do an inverse FFT. And lo and behold, there's that one block down there in the corner, which is one of the 256 possible states that says, here are all the shift bits. Here's how it was shifted. And this is all done in parallel. This is done very quick. Now you say, okay, fine, you can simulate this. How do you know it would really work? Well, Martin took this and ran it on both the IBM Experience 5-qubit machine and on the University of Maryland ion trap machine. And we took a 4-qubit version of this. And sure enough, we get fidelities out. We actually get the shifts coming out. We can see through tomography how well this works with noise. And it works. That's the point. And there's a paper on all of this. My area is more on the quantum chemistry side. So I'm going to spend a little time just describing it. The upper right is the equation, the Hamiltonian that describes how electrons move. All you need to know is where you see the dagger, an electron shows up there, and where you don't see a dagger, it disappears. So it went from orbital Q to orbital P, and the magnitude of it moving was HPQ. So there's just a bunch of constants say, this electron likes to hop from here to here with this probability. The second one is two electrons doing the same thing. So there's electrons in R and S, and they wind up hopping to P and Q. If the indices are the same, let's say P equals Q, what's the probability of the electron not moving? So that's it. That's the whole equation. It's really hard to model. This is, like I said, 50% of supercomputer time out there is doing this sort of equation. In fact, this exact equation, over and over and over. It's very, very hard, because the state you build is one of these exponential states to actually do it right. So we took a look at the quantum algorithms that were proposed, and they were ridiculously long on a quantum computer to do. And so there's 4 papers here that we did over the course of the year trying to get it better. And what we did, we took as our poster child Fe2S2. This is 2 irons, 2 sulfurs, very tiny little molecule, 4 atoms in it. It's actually very important. It's in your hemoglobin. It's also in photosynthesis. It's got 4 little pigtails on it that can pick up other molecules and move them around. It's an energy transport molecule. We would love to be able to analyze this. We can't. It's got iron in it. So this is one of those with d orbitals that you just can't do on a classical machine, period. It's intractable. So we look at the assumed scaling for a quantum computer with reasonable assumptions, and it came out to, oh, we can get an answer in 24 billion years. This is where the pointy-haired boss gets mad at me and goes, I can't sell that. No, I can't either. So the first paper we did, we got it down to 850,000 years, a little better. Next paper, we got it down to 30 years. And everything we did here are normal things you would do in software. We got rid of redundancies. We did parallelization. We did pre-computing. We got rid of redundant calculations, on and on and on. All the things you would normally do. But then we dropped this to 5 days. And then we dropped it to 1 hour. Huh? That's kind of a ridiculous reduction. How'd that happen? Well, I said we can only simulate up to about 30 qubits. And I can't do very big molecules like that. But it turns out even the little molecules give you pointers to how well your estimates go for the big molecules. So the blue line at the top is the initial scaling that people assumed. There's the first paper and the second paper. But during this time, I'm using liquid to simulate those little molecules, and I'm getting that red curve at the bottom. Not even close. So we go back to the theorists. Then we say, what's up? Say, well, we made worst case assumptions on everything. Well, nature doesn't use worst case assumptions. There's symmetries, there's efficiencies, there's all sorts of things nature does when, atoms come together and make molecules. And sure enough, by changing the assumptions to something that matched nature better, that's the third and the fourth paper, they come right down to what we were simulating. So even with a small simulator, there's a lot you can do in terms of improvements, in terms of understanding what the real costs, what the real algorithms are going to take to do. And I should mention that molecule we had on the supercomputer for doing nitrogen fixation also fits in about an hour. This is the one with the 6 irons and a molybdenum. They all fit in about the same space. I want to mention materials. I'm not going to put a lot of detail here. We're going to run out of time, and I'd like to leave time for questions. So materials are actually easier than doing chemicals. And the reason is they have a regular structure. They have a lattice. And typically, the lattice sites just interact with things that are near them in the lattice. So you can do much more efficient calculations. But the types of models that are done on the classical machines tend to only have a couple of characteristics to them. We can't really get to the types of materials we care about. And what we're going to do is take a single site on the lattice. They're all the same, but we're going to pick one and call it special. And then we're going to get rid of all the others, do like a mean field approximation, where we just take all the rest, we approximate them, and say, how does that interact with this guy? Now, if we just do a mean field approximation, we lose all the quantumness. It becomes classical. But if we do that mean field, or how things hop on and off, but at every frequency. So keep all the different frequencies that things might hop on and off, and come up with a coupling strength. It stays fully quantum. We actually don't lose anything in terms of modeling. And this is what we do on classical machines today. So this is called an Anderson impurity model. And for the impurity, that special site, we can make it as complex as we want. So that's the same quantum chemistry Hamiltonian we had up on the screen. And we can do really complicated things here because we're not going to do the rest of the lattice. So we can afford to make this one really complicated. Then we're going to create a bath that we architect that's going to hop on and off that impurity. And then the model of the bath itself. By keeping all the frequencies, this is known as dynamical mean field theory. I really don't care for you to remember any of that. The important piece is what's coming up now. This is how you actually use a quantum computer. We're back to practical application. We're going to make this model, that equation you just saw. We're going to posit a model that all the values are. And now we're going to send it to a coprocessor, just like you would in the cloud, just like you would with GPUs. But the quantum machine is the coprocessor. That's how it's going to get used. It does certain things really well. We've seen low input and output, high computation, where I can load that model efficiently, do a bunch of computation. What comes back is, how well does that actually model the material I'm interested in? I can then do a standard calculation called a self-consistency equation, which then lets me update the model. This looks just like standard machine learning. Put in a model, check it with the environment, bring it back, update the parameters, rinse and repeat. This works extremely well. Again, this is the type of thing we do all the time on supercomputers today, but we don't have the quantum coprocessor there. We're doing all the heavy lifting on the classical machine. So what you do is you extract out those really hard computational parts, do them on the quantum machine, and now this whole thing runs ridiculously faster. There's another piece of this that's even more important. We didn't get one answer out, which is what we typically do with the examples I've given so far. We got a model back out. We have a classical description of the quantum model that can be loaded efficiently on a quantum computer. Now I can load that and get ground states, energized, and energy, excited states, excuse me. I can get catalytic rates, diffusion rates, all sorts of things, because I have a good model of the molecule now that I couldn't get before, or of the material. So this lets me build something I can then ask future questions of on the quantum machine. That's cool. I can also use the same type of loop for something completely different. This is a variational eigensolver. The difference is, instead of loading the whole equation, the whole Hamiltonian on the bottom, I'm going to load little pieces. Remember, it's made up of all these sums? Well, let's put each one of the sums in separately. Now, the good news is I have something that only has to stay coherent for a short period of time. I can use physical qubits. I can use today's really lousy qubits for this. Doesn't matter, because I'm going to just only do a few hundred or 1,000 gates. And then I'm going to add up all the results. This is a standard technique in quantum physics people do all the time. The bad news is you're sampling to figure out these parameters. So to get 1 over n error, I need n squared samples. So very quickly, if this gets big, you can't do it. But for small initial machines, this gives us something that lets us use physical qubits, actually do real problems. They're not things you couldn't do classically, but they show they work. We can make useful things with a quantum machine, and there may be a sweet spot that you can get just big enough that you can solve something you can't do classically. Example, ozone formation needs about 36 qubits, and we've only been able to do it classically for about 4 years. There's this thing about if you have 2 oxygens and another one comes in, does it bounce off? Does it go into a van der Waals orbital? Does it become ozone? And it's a very difficult phase diagram to actually come up with, to actually figure out. And that's a really small number of qubits. And we couldn't do it classically until very recently. So this gives some hope that we can do some things like this. So I'm going to wrap up with, hopefully I've given a feel that there are some real world problems that look like quantum really matches well. There are a lot they don't match. The nitrogen fixation, we today use up 5% of the planet's production of natural gas every year to make fertilizer. 3% of the energy output of the planet. This makes it so lots of developing countries can't even afford to plant crops because they can't afford the fertilizer. But there's a little anaerobic bacteria sitting in the roots of all the plants out there that does this every day at room temperature, room pressure, and that nitrogenase or FeMoco complex that I had up there is how it does it. If we can analyze it, we could make a room temperature, room pressure, something that didn't have to be anaerobic, go in an atmosphere and make an industrial process that was cheap and worked, but we can't analyze it. We can't simulate it. We can't figure out how to play with it. And we've been trying for 20, 30 years at this point. Carbon capture, by the way, you need about 200 logical qubits to do that. Carbon capture, same problem. I can make a paint. You paint everything in the world with it, it sucks the carbon out of the air, that's the end of global warming. Same scale problem, about 200 qubits. Materials, 500, 700 qubits, something in that range, logical qubits. But we lose 15% of the power grid in this country just sending power over lines, over the power lines. Room temperature superconductors would fix that, not to mention all sorts of other things. We can get better batteries that don't need heavy metals, smart materials, there's all sorts of things on that end. And since I'm at Microsoft, again, the pointy-haired boss comes in, they want machine learning. So I have to give them machine learning. That's actually my current research area. This is in the 1,000 up number of qubits that you need. But it does look like there's some possibilities. I've got all sorts of little quantum systems that now learn to solve machine learning problems. We'll see if it's better. If we get better models, we'll see what it looks like. But it gives you an idea that there are lots of real-world problems that are possible to solve here. And I come to work every day with the greatest group of people all over the world. Unfortunately, I have Skype meetings that start at 5 in the morning because they're in Europe, and then go late at night because they're in Australia. And then I'm on the road all the time. But it's a wonderful team of people. Some are doing basic research, some all the way out to just how do you engineer a new refrigerator? How do you make these things efficient enough? How do you make the wires that you need? There are all sorts of really interesting problems that go across this whole thing to make a practical machine. And as I promised, I'd give you a pointer to where that quantum development kit is. It's the only URL you need. Everything we do is under Microsoft.com/quantum. So you'll find all the documentation, all the press announcements. You'll find a pointer to the quantum development kit. You'll also find a newsletter that's a low-touch newsletter if you want to sign up for it, that just tells you when there's an announcement, when things actually happen. And I thank you for your time.